know at this point. And today we're going to look more about how to evaluate these structures and how we can actually find the best structure, not just one that is basically correct. So let's take a look at each of these. I'll do it on the computer so it ends up online. So we'll look at carbonate first. Carbonate ion. We didn't talk about ions, fluid structures of ions last time. So did you figure out what do you do with that -2? Yeah, we got to add 2 electrons because -2 means 2 extra electrons. So when we count our total electrons, we're going to count 4 from the carbon for valence electrons, 6 from each oxygen, and then we've got to add an additional 2 for the 2 minus. So our total number of electrons is 24. All right, then we set up our structure. This one is, you can probably guess how things are connected. The carbon's in the middle, with the oxygens around the outside. With Lewis structures, we don't worry too much about the bond angles and how we draw those. As we'll see in the next chapter, we actually can sometimes predict those bond angles. But whether you drew them 90 degrees all the time or kind of spread them out more, at this stage it doesn't really matter. So there's how we would kind of put this thing together. 24 electrons, we've used 6, so we've got to get 18 more in there. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's all my electrons. And what do you see? Carbon only has 6 electrons. So carbon doesn't have an octet here. This is not a good situation for carbon. So we have to fix this without adding any more electrons. We talked Tuesday about how to do that, which is, we have to share more electrons. We have to add an additional pair of shared electrons that we call a double bond. So we can choose whatever to do that. Maybe we'll take that one, and we'll put it here. And then we have a nice structure that fits all the rules. Because it's an ion, it's also important to show that we did indeed make an ion. And so when we make a Lewis structure for a charged species like that, we're going to wrap it in brackets and show that it is charged, just like we would with an ion, with a monoatomic ion. All right, questions about that structure? So I drew this way, and I put that double bond over to the right. Did anybody draw it but put the double bond to the left or down or up or somewhere else? Up? Anybody else? Down, up, yeah. Does it matter? Okay, so that's correct. Does it affect the overall structure? In other words, would this be a different molecule if we go all the way down to the molecular level, if that double bond switched from one spot to another? I mean, all the way down at the molecular level, it would, right? Because if you're actually looking at a single molecule of carbonate, if there's a double bond here that goes to this oxygen, and there's not a double bond that goes to this oxygen, and not a double bond that goes to this oxygen, that's different. Those are different atoms. They're maybe chemically equivalent on average, but those are different atoms. So if we were to, say, do some spectroscopy on this ion and actually measure the bond lengths, based on this structure, we would expect to see 1 double bond and 2 single bonds. But when we do those measurements, we don't see 1 double bond and 2 single bonds. We see 3 equivalent bonds. And the reason for that is an effect called resonance. So I could have drawn this in 3 different ways, besides all the changing of angles and all that stuff that we also could have done. I could have drawn that. And I could have drawn this. Those are all acceptable Lewis structures. And we would say they're all chemically equivalent. They all show basically the same type of molecule. but they're not technically perfectly the same. One thing we can do in chemistry is called isotopic labeling, where we could actually change out some of those oxygens with a different isotope. So use oxygen 18 instead of oxygen 16 or something. And then we would see, is that double bond connected to the oxygen 16 or the oxygen 18, or is it an average of both? And so it's not these aren't technically the same. They're called resonance forms. And what that means is that the actual real structure of carbonate is a hybrid of these three that we've drawn. So if we actually look at data for carbonate ion, we find 3 equivalent CO bonds, each one in between a single and double bond, about the length of 1 1/3 bonds. So there's no such thing as 1 1/3 bonds, but that's basically what we see. So that tells us that the actual structure that we're looking at is really a hybrid of these 3 resonance forms. And anytime you have this situation, you have this thing called resonance, where you can make a structure that is a hybrid of the three. When we draw it on paper, we still generally draw one of those forms, or maybe all 3 of them, because it's hard to draw a resonance hybrid. The book kind of tries a little bit. You can do something like this if you want, where you use like dotted lines to represent partial bonds. You'll see that sometimes. But it's still hard to do the electron accounting. When Lewis developed this theory, it didn't really account for these types of structures. So that's why we have to kind of do weird stuff to deal with that. So we call this resonance. The word resonance actually is a little bit of a misnomer. Resonance means alternating back and forth between something, like moving back and forth. And the original theory of this was that there was flipping going on, that the double bond was like flipping around the molecule. Now we know that's not really true. It's actually the molecule is just a hybrid of the 3. But originally I thought that it was flipping all around. And so that's why it's called resonance. It's still called that. It's a really important part of organic chemistry, of thinking about structure in this way. And so it's something that you'll probably use in the future. Excuse me. In this class, we're going to recognize it, and we're going to also use it to predict some chemical behavior. So take a look now at the rest of the structures that you wrote, whether or not you think they're right, and see if you think any of the other molecules might have other resonance forms. So other ways of drawing them that preserve the same connectivity, but have the electrons distributed in a different way. And while you do that, I'll write that definition down here. So resonance forms are going to have the same atom connectivity, but a different arrangement of the electrons. So you can't disconnect the atoms and move them around. You keep the same connection. But if you can have structures that fit the rules, that still maintain octets on the atoms that need them and so forth, but the electrons are distributed in a different way, then those are resonance forms. So did you find any? Any of these ones that you drew before have resonance forms? Maybe, maybe not. Well, let's see, what'd you find? O3, yeah, O3 has resonance forms. So let's do that one next, so we can take a look at its resonance as well. O3 is ozone. So we're going to add those up. That's 6 valence electrons for each oxygen times 3 is 18 total electrons. So we'll connect our OOO and then fill in those 18 electrons. 1, 2, 3, 4, 5. Well, we'll start with 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we end up with that same problem. That middle oxygen does not have enough electrons. So we have to take 2 from one of the outer ones and share them with the middle one so that they end up with the right number of electrons. And we could have written that like this. So that shows that this is resonance. So we would expect that those bonds in ozone are not actually a double bond and a single bond, but they're each kind of 1.5 bonds. So they're in between double bonds and single bonds. There's a hybrid that is a average of both of them. Like this. That one. That technically works. Yeah, and then a lone pair, 2 lone pairs on each. Yes, this technically works, but that is not a stable structure because of the strain involved in the ring and like trying to close those angles up like that. So at this point, yeah, that's fine, but ultimately that's not a structure that works. So this one does fit the rules, but it is not a real structure. Also, we should say that is not a resonance form. So that would be what we call an isomer, a different way of connecting the same atoms, but not just a change in electrons. Because now the atoms in that other one, the atoms are connected in a different way. All right. So now let's take a look at N2O. Which might pose a little bit of a problem for us, because there's a couple different ways of connecting these atoms. We could go NNO, and then if we fill in the electrons, that would be 5 for each nitrogen, so that's 10 plus 6 is 16. So 2, 4, I think we're going to end up needing a couple double bonds here. Right, like that. This one also has some different resonance forms we could have drawn. Like this, or like this. And beyond those 3 resonance forms, we also could have connected these in a different way. We could have gone NON and had basically the same situation where we have some resonance forms for that too. This one would only have one resonance form because the 2 sides are equivalent. So that's a lot of choices, right? I mean, really it's 2 choices because resonance forms are always resonance forms. But even within the resonance forms, unlike the previous examples, ozone and carbonate, the resonance forms are not equivalent, clearly. There's definitely a difference between a double bond between nitrogens and a double bond between N and O, or a triple bond between nitrogens and a single bond between N and O, or a single bond between nitrogens and a triple bond between N and O. That's going to drastically change that structure. And so we can't just say that the overall structure is an average of them, because some of those might be better than others. Some of those might be more stable than others. In the previous example, they were all clearly equivalent. They were all chemically equivalent. They were all the same basic things, just in different orientations. These now, we have actually different ways of connecting these atoms, plus we have two structures to choose from, which I'll separate a little bit here, which are not even resonance forms. So the ones on the left and the ones on the right are not resonance forms. So how do we decide which is correct? Because everything I've drawn there fits our rules, right? Everything has 16 electrons. Everything has octets on nitrogen and oxygen. So how could we figure out what the right structure is? And the answer is we can use a type of electron accounting called formal charge. We've seen now a couple different ways of accounting for charge. One is just the charge, which is like an ion has a charge. It is a charged particle. But we've also seen oxidation states, which are not charges, but are kind of an accounting system for how electrons are shared in a bond. We've seen partial charges in polar molecules on Tuesday. It's another way of kind of accounting for that. And so this is another one of those things where it's not exactly a real physical quantity, but it's a way of looking at a structure and saying, okay, probably this area of the structure is more electron rich, and probably this other area of the structure is more electron poor. And we can use that to make decisions about that exact problem that we just talked about. All right, so here's how you calculate formal charge. You take each atom and for each atom, the formal charge is, make sure I'm doing this right, the number of valence electrons for that atom, not in the compound, in the free, the valence electrons in just the free atom, minus the sum of the number of non-bonding electrons and the number of bonds connected to that atom. Doing that calculation gets you this formal charge. So, as an example, let's take our, before we look at the nitrogen ones, let's go back to that carbonate ion. I'll just use one of the ones here that we drew. And so for each atom, we want to calculate a formal charge. Let's start in the middle with the carbon. So the number of valence electrons on carbon is 4, right? Yeah? Okay. And then we're going to subtract the number of non-bonding electrons, which in this structure is 0. You don't see any dots around that carbon, right? And the number of bonds connected to that carbon, so 1, 2, 3, 4. And that gets us 0. So that says that that carbon has a neutral formal charge. Its formal charge is 0. Neutral formal charges are, generally speaking, the more stable way for an atom to be. Okay, so now let's look at one of these oxygens. How many valence electrons is 6? And now we've got a whole bunch of non-bonding electrons. There's 6 and a bond, 1. So that's going to be -1. So our formal charge on that oxygen is -1. And then any oxygen that's in that same situation is going to have that same formal charge. So we can look at the other oxygen there on the bottom and say, okay, well that one must have the same formal charge because it also has 6 It's still oxygen, and it has 6 non-bonding electrons and 1 bond. So also a formal charge of -1. So then we just need to check this other oxygen since it's in a slightly different situation. 6 valence electrons, 4 non-bonding electrons, and 2 bonds. And so that one's formal charge is going to be 0. So what we've discovered here is that there are 2 -1 formal charge oxygens and 1 neutral formal charge oxygen. And so we would say, okay, that makes sense because it's a 2- ion. The formal charges should add up to the overall charge. So if we add all the formal charges in the molecule, 0 plus 0 plus -1 plus -1, we get -2, which is the overall charge on the carbonate ion. Formal charges are often just listed like I've done it here, but they can also be drawn as a charge with a circle around it to separate it from an actual ionic charge. So we would draw a minus here and a minus over here to show that those are the 2 with the formal charges, and we usually just leave off the 0 formal charges if anything is neutral. All right, so what does this tell us about this molecule? Well, we know it's a hybrid, but we also know now that the electron density is greatest around the oxygen. Now that's predicted from electronegativity, but it's also confirmed by formal charges, that the oxygens we're basically saying have more electron density than they'd really like ideally. So when we look at judging Lewis structures, formal charge can be a powerful way to figure this out. Because in general, and again, there's always exceptions, there's always other things going on. I should reword that. In general, we want to minimize formal charges. More stable molecules, in general, will have lower formal charges. So if you can get all the formal charges to 0, that's usually the best way to do it. If you can get most of them to 0, that's better. If the fewer formal charges you can have, if you have some choices on how to draw a structure, the better. And then the second rule for formal charges generally is that we want to put negative formal charges on the more electronegative atoms. So if you have a structure where you have a choice and you could put you got to have a negative charge, but that negative charge could either go on nitrogen or oxygen. You're going to preferentially put that negative charge on oxygen, or you're going to pick the structure or the resonance form where the negative charge is on oxygen, because oxygen is more electronegative than nitrogen, and it's better able to stabilize that negative formal charge. And in general, again, formal charges greater than in magnitude than plus or minus 1 are usually very unstable. And again, that's going to change a little bit depending on what kind of atoms we're looking at, but in general, if you have come up with a structure and you got to put a 2 plus or a 2 minus formal charge on that structure, on an atom in that structure, chances are that's not a great structure. It's not going to be a very stable structure. All right, so now that we know these rules, let's go back and revisit our N2O nitrous oxide structures. And I want you to assign a formal charge to all the atoms in those 5 structures that we looked at. Now remember, that doesn't mean you need to do the calculation every single time for every single atom. Look for some similarities. If you find an atom that's in the same position in each case, that has the same type of atom, same number of non-bonding electrons, same number of bonds, it's going to have the same formal charge as whatever one you previously calculated. So go through and calculate those. See what you get. Come have some candy or coffee if you want to. Solid. All right, so did you get something like that? Those are kind of small to see up there. So looking from the top left, that's minus, plus, minus in the first structure. Then down below that, the resonance form just has plus and minus. And the one on the bottom has 2 minus, plus, and plus. The one on the upper right has minus, 2 plus, and minus. And then the lower one is 2 plus and 2 minus. Any issues with those? Okay, so now let's look at those numbers and use that to make some judgments about what the better structures are. So first off, based on our rules, which structures are probably not major contributors here? The what? Yeah, the ones with plus or minus 2. So I'm not going to like get rid of them because they're fine in terms of like they exist, but I'm just going to put parentheses around them. So we can say like these are technically correct Lewis structures, but probably not major contributors. But this already answers a big question of ours, which was which of these two ways of putting the structure together is correct. And this really shows us that that way on the right, NON, can't really be correct. That can't be the proper connectivity. There wasn't really a good way of knowing that without looking at the formal charges, because just looking at the electron counts, they looked fine. And actually, that one might have looked a little better because it was nice and symmetric. But when we look at the formal charges, there's really no way to make the formal charges work out in that column on the right. And so we would say that this is probably not the correct connectivity, and in fact, it's not. So that structure doesn't really exist. That's not an N2O. And we use formal charges to figure that out. So then let's turn our attention to the correct structure, which is the one on the left. Which of those resonance forms is probably the most stable? The second one, why? Right, it has the fewest formal charges, and the negative charge is on oxygen, the more electronegative element. So if we looked at the actual structure of N2O, we would expect to see a structure that looks more like the second one than the first one. So again, it's going to be a little bit of an average, but it's not going to be a true even average. It's going to be a weighted average, where that middle structure is really the most important part of the structure. And the other ones also contribute. And let's, I probably should have checked this, but let's actually see if that's true. So you actually see both of them. Wait a second, what did I do wrong? Oh, that's because I did this wrong. That should be, why don't you guys catch me? That should be positive, that should be a neutral formal charge, right? Because oxygen 6 minus 4 minus 2 is 0. So the second one still probably seems a little bit better, but we expect a little bit more of a hybrid between the two. And I think that's true. I'll try to look that up and see. This final one down here is probably not an important contributor to the overall hybrid. So the hybrid is likely a weighted average of these two, not so much of this one, because of the 2 minus formal charge. All right, that works. Okay, let's try this. So this time, try to draw a structure for NO2. This is nitrogen dioxide, not N2O, but NO2. And this time, now that we know all this stuff, when we draw a Lewis structure, we want to draw resonance forms and include all formal charges. So when you draw a Lewis structure from this point forward, you want to always be thinking about what other possible resonance forms could I draw, and always include the formal charges. All right, get some structures, John. Don't forget about those formal charges. Did anybody find any other structures? Any other resonance forms that I'm missing? Wait, we got another problem here, don't we? Yeah, there's 17. So, that's right, 2, 4, 6, 8, 10, 12, 14, 16, 17, yeah. Sorry, so this does exist, and it's one of the reasons that Lewis structures are not always super useful. But what I was actually thinking of here was the nitrite ion. So let's just pretend that I said this instead. We will talk about odd electron species. Odd electron species pose a big problem because you can't have some atoms not going to have an octet if you have odd electron species. And so even if they exist, like, what are you going to do about that? And that's why we actually need better, sometimes we need not necessarily better, but we need a theory that can accommodate those things, and that's what we'll look at in the next chapter with molecular orbital theory. But let's pretend that I said nitrite ion, NO2 minus, instead. And in that case, our two resonance forms are correct, right? Anybody find any other resonance forms? We can't put triple bonds anywhere. We can't do like what we did for N2O because we've got too many electrons now because of the extra oxygen. And we should have a negative formal charge on one of the oxygens because we know the overall structure is going to be negatively charged. Is one of those resonance forms better than the other one, or are they equivalent? Better meaning more stable, or are they equivalent? They're equivalent, right? Because they're basically the same. Everything's kind of in the same chemical environment on both sides, same kinds of formal charges and so forth. All right. Let's try another one. Scn minus, thiocyanate ion. Same thing. Draw resonance forms, draw formal charges. thing that's helpful as you're studying these things, if you're drawing structures like this, drawing resonance forms, work together with people, but first work on your own. Draw the resonance forms you can, do the formal charges, and then compare to the people that you're working with. And that can be a good way to be like, oh yeah, I missed that one, or oh, I missed that one. And then you can talk about those. And if you keep missing the same types of resonance forms, you keep forgetting to do those, but you're working with somebody who doesn't, then that's a good way to check yourself on those. All right, do something like that. So you may have also noticed in this structure that if you try to connect those in a different way, like if you try to put sulfur or nitrogen in the middle, it doesn't quite work out. You get weird formal charges, or you have trouble satisfying octet rules, or whatever. If you really want to minimize formal charges, you have to keep that connectivity SCN. So again, like before, we're going to count, this is technically a resonance structure, but it's probably not so important because a lot of charges and a big 2- on that nitrogen is probably not going to be an important part of the overall structure. The other two will, with a negative charge either on the nitrogen or on the sulfur. If you had to judge those two based on formal charges, which would you pick? The top one? Why? Or I mean the middle one? Oh, you said the bottom one. Why?
I was going to say if S is more. Oh, no, it would be there.
So bear with me on this one a little bit. Based on what we just said, you would think, if we look back at our electronegativities, nitrogen is considerably more electronegative than sulfur, which makes it seem like that negative charge should go on the nitrogen. In this case, it's one of those things. It's actually not the case. Again, I wouldn't have expected you to see that at this point, but the reason is sulfur is so much bigger than nitrogen. Larger atoms can better stabilize charges than smaller ones because the charge density is lower. The charge basically has a bigger area to spread out on a larger atom. And on a smaller atom, the charge is very concentrated. So even though, yes, nitrogen is more electronegative, in this case, that larger, what we call polarizable sulfur, can better stabilize that negative charge. So the bottom one is a little bit more of a contributor to the overall structure. But I wouldn't have asked you to figure that out at this point. Did you at least get the structures right and get some formal charges on them? Good. And remember, these are resonance forms. Resonance forms are usually shown with double-headed arrows between them, as opposed to single-headed arrows, which indicate a chemical reaction. All right, so for the last bit, we're just going to talk about some of the exceptions that we see. We talked about a couple of these on Tuesday. On Tuesday, we talked about how boron and beryllium generally only make 3 or 2 bonds. So they will generally have less than 8 electrons around them. So as an example, the structure BF3 looks like this. Even though we could take those electrons from the fluorine and make a double bond to boron, that would give boron a negative formal charge and fluorine a positive formal charge. But the actual structure is more like this. Actually, the actual structure, these molecules come together and form a double, a dimer. But we say that boron has is okay with less than 8 electrons. So boron Lewis structures will generally be drawn with less than 8 electrons, with 6. The other problem that we just looked at earlier, odd number of electrons, so like NO, which is a real structure. There's really no way to draw that with following the octet rule. So we can go, so we can do something like that, and like this, and then there's this extra electron. And so nitrogen here doesn't have a formal charge, but it also doesn't follow the octet rule. There's just no way to avoid that. We got an odd number of electrons, we can't make a good Lewis structure. And that's just a failing of the Lewis model. Lewis's theory was that electrons need to be paired up, that there's something important about electron pairing. And that turns out not to be true. So there's plenty of molecules where that doesn't work. And there's just, what are you going to do? So I'm just going to put a big question mark there. There's no great solution to this except it's just a failing of the Lewis model. So we do what we can. In the next chapter, we'll see the real solution to that. All right, and then the other exceptions is anything in the third row and below, third row of the periodic table and below, can have more than 8 electrons around it. So we're not limited to 8 electrons. So we get what are called hypervalent species, which are things like SF6. That's a real compound, perfectly stable. And we usually draw it like this. That sulfur clearly does not have an octet, right? It's got 12 electrons around it. But turns out, not such a big deal for sulfur. In the next chapter, we'll get into some of the theories as to how this works and why these atoms can do it this way. It's not simple. There's not an easy answer. The book kind of pretends that there's an easy answer, but it's not. It's something that's still debated and still measured today as to what the bonding actually looks like in these things. Another way that this is somewhat complicated, if we try to draw a Lewis structure for sulfuric acid, H2SO4, we can draw a Lewis structure like this. So we put our O's. We know we can't put the H's in the inside at all because hydrogen can only have one bond. We can put the H's like this. Put our lone pairs in. And that follows the octet rule. But the way we have this drawn, right now, there would be a formal charge here and here on oxygen, and there would be a +2 formal charge on sulfur. So if we care about minimizing formal charges, we should draw this as a resonance form that violates the octet rule. So if instead we draw, whoops, losing electrons here. If instead we make double bonds to the oxygens like that, now we have neutral formal charges all the way around. So we don't have those minus and plus formal charges. But sulfur has 2, 4, 6, 8, 10, 12 electrons around it. Again, violating that octet rule. So for a long time, the idea was, well, you should always draw it like this because it minimizes formal charges. And when the criteria is you should minimize formal charges, that is correct. So like when you're doing homework and stuff, and they say draw the Lewis structure that minimizes formal charges, that's the right way to go. But now we know from measurements and things that that's not really the correct structure either. There's sulfur and oxygen don't quite double bond in that way that we would expect in a structure like that because their orbitals don't really combine in that way. So from a real like what's actually happening chemical perspective, that structure is a little bit more troubling than the other one, but that is the one that minimizes formal charges. So make sure that you know your criteria when you're talking about these things or when you're trying to answer these questions. In general, at the general chemistry level, the criteria is minimize formal charges. That's kind of the rule of thumb. But as you can probably tell, I have a little bit of a problem with that because of how it fails to reflect the reality of these compounds. But I'm also dressed as a penguin, so what do I know? Okay. And then the last part, the last thing that we're going to talk about with regard to these types of structures is bond lengths and energies. Throughout today, I've been saying things like, we know this because of measurements, we know this because of whatever. And the way that we're often looking at that is by measuring the energy of a bond, by either breaking it and measuring the amount of energy it takes to break it, or forming it and measuring the amount of energy it gives off to form it. Or we're looking at bond lengths, which are also related to the type of bond, whether it's a single or double bond. So when we're trying to see, for instance, in a carbonate ion, what are those actual CO bonds like? Are they single bonds? Are they double bonds? Are they in between? We're looking at bond energies and we're looking at bond lengths. So these aren't things that you need to memorize, but just to give you an idea of what kind of numbers we're looking at, let me show you a table of bond energies that we will use, or that you'll use in your homework to do some calculations. And we'll practice this a little bit downstairs today too. So here are some bond energies. I'm just going to put these over here. In kilojoules per mole. So if we look just at the top left there, a hydrogen-hydrogen bond, that tells us that if you want to break a mole of hydrogen-hydrogen bonds, you have to put in 436 kilojoules of energy. If you form a mole of hydrogen-hydrogen bonds, you give off 436 kilojoules of energy. So those numbers, the sign of those numbers, whether they're positive or negative, has to do with whether the bond is being formed or broken. So one thing we can do is if we look at a reaction, if we look at a chemical reaction like, let's see if I can fit this in here, CH4 plus Cl2 goes to CH3Cl plus HCl, and these are in the gas phases. We can look at that reaction and say, okay, what's happening here? This is all covalent, so it's not like precipitation reactions or whatever. But we can say in this reaction, a CH bond is breaking, a CL-Cl bond is breaking, and a CCl bond is forming and an HCl bond is forming. See that? That might be clearer if we actually draw the Lewis structures. So CH4 like this, Cl2 like this. I'm going to leave off the lone pairs for now just so we can see it. CH3Cl and HCl. All right? So if we look at those Lewis structures, think about the ones on the left that are breaking. So a CH bond is breaking. A Cl-Cl bond is breaking. Maybe we should draw a little slash sign to show those are breaking. And then a CCl bond is forming and an HCl bond is forming. And most covalent-based reactions can be thought of in this way, as bonds breaking and bonds forming. Does everybody see the bonds breaking and the bonds forming in this one? So we can actually find the overall energy of this reaction. Is it exothermic? Is the energy given off? Is it endothermic? Is energy taken in? We can figure that out by just looking up these numbers and adding and subtracting. So let's do that here. So we want to know a CH bond is 414 kilojoules per mole. A Cl-Cl bond is, thank you, 243. I didn't see that one. Oh, there it is. Okay. A CCl bond is 339. And an HCl bond is 431. And again, you don't have to remember these numbers. You'll have access to these tables if you need them. So the overall energy given off by this reaction, we're going to put a negative sign on the bonds that are formed because forming bonds gives off energy, and a positive sign on the ones that are broken. And so the overall heat of reaction or enthalpy of reaction, which is called delta H, is going to be the sum of those things. So 414 plus 243 minus 339 minus 431. And if you do that calculation, you get minus 113 kilojoules. So if you do a mole of this reaction, you will give off 113 kilojoules of energy based on the bonds that are broken and formed. And that's it. If the reaction has coefficients that are not 1, so you balance the equation and you end up with coefficients that are not 1, what do you think you do about that? Right, because all these are per mole, so you're going to multiply based on that. And there's lots of examples of these in the homework that you'll see. All right, so I'll see you downstairs in about 15 minutes. One thing about the homework, the mastering chemistry system doesn't do a great job with drawing Lewis structures. The system just doesn't work that well. So we've had so many problems with it in the past. I've made chapter 9 just practice, so it's not graded. This also